Good morning and welcome to our next to the last unit, which happens to be all about confidence intervals. And at first glance, confidence intervals may be something that you think you've never heard of before. I want to assure you, you experience them all the time. People just don't call them that. So the most likely occurrence where you have encountered confidence intervals is when dealing with the weather. So anytime here in Kentucky that we are expecting snow, the weather can be very unpredictable, right? And so the weatherman doesn't say, we are getting 2 inches of snow tomorrow. What he tells you is, I think we are getting between 1 and 3 inches of snow, right? So 2 may be in the middle of that interval, but he doesn't give you an exact answer. He gives you a range of possibilities. That right there is a confidence interval. Okay, so a confidence interval takes a sample, or it looks at the data available and it says, you know what, we can't be 100% sure about anything, but we can say with a certain level of confidence that our answer is between this number and this number. So let's look at an example. Let's say that we were looking at a group of test scores. Let's say it's for this STA 220 class, right? And so I decided to give you 5 random test scores from our class. So I'm not giving you the entire population. I'm giving you a sample of size 5, and you can see those scores right here. Okay? And let's say that I told you, based on those 5 scores, I want you to estimate how our class did on this test. Well, what you would probably do first is you would find the average. And the average comes out to be 77.4. So here's what I want to remind you of. If we are dealing with a population, so if we knew everybody's test scores from this class, we would have a parameter, and that parameter would be the Greek letter mu, which stands for the mean. That's not what we're dealing with here. I gave you a sample of 5 scores, right? So if I only have a sample, this number 77.4 that we just calculated is a statistic. And so the statistic that we use to stand for mean is X with a little bar on top of it, and we call that X bar. Okay? So here's the issue. Just because I gave you 5 scores and you found that the average was 77.4, that doesn't mean that the entire class average was 77.4, right? Because what if you just happen to get a sample of really high scores, right? So what we do is we build in what's called a margin of error. And there are exact formulas for that. We'll get to those later. But for now, let's say that you decide, a reasonable margin of error would be to say maybe our average was off by plus or minus 5 points. So maybe the true average could be 5 points below 77.4 or 5 points above that. So then we build a confidence interval and we say we are reasonably confident that if we got a sample average of 77.4, then the whole class average was somewhere between 72.4 and 82.4. That's our confidence interval right there. Okay? So then a reasonable question would be, well, how confident are you? And that would vary. What we do in statistics is we have specific formulas, and again, we'll get to those in a minute, that allow us to be 90 or even 95 or 99% confident as to what our answer truly looks like. Okay? So let's say that I gave you a different sample of 5 scores, and that confidence interval came out to be 71 to 79. Okay? What would that mean? Well, a confidence interval is built off of what we call a point estimate, right? Which in this case, our estimate happened to be an average. It's not always an average, but in this case it is. So if I gave you an interval from 71 to 79, what must have been the point estimate that came from that sample? Well, 75, because that's halfway between 71 and 79. And what would your margin of error be? It would be 4, because you can go 4 above 75 or 4 below 75. Okay? So the way you build a confidence interval is you find the midpoint, and then you choose your margin of error, and you add it from that midpoint, and you subtract it from that midpoint. Okay? So question number 7 says, Miss Gallus claims that the true average score on this exam for the whole class is an 84. Would our confidence interval support this claim? It would not support it, because even allowing for 5 points on either side of our point estimate, 84 is not included in our confidence interval. So when you're looking at a confidence interval, what you're looking for is for your suspicion or your hypothesis to either be included in that interval or to not be included, to give you an idea of if your idea is correct or if it's not. Okay? Okay, so let's look at an example of how we interpret confidence intervals. So the Pew Research Center and Smithsonian Magazine recently quizzed a random sample of 1,006 U.S. adults on their knowledge of science, and one of the questions asked, which gas makes up most of the Earth's atmosphere? Hydrogen, nitrogen, carbon dioxide, or oxygen? A 95% confidence interval for the proportion who would correctly answer nitrogen is 0.175 to 0.225. So let's talk about what's happening here. We're not going to every U.S. adult, right? That would take far too long and it would be impossible. So what did these companies do? They sampled 1,006 adults, and then based on the percentage that answered that question correctly, they built a confidence interval to predict what the entire population would do. Okay? So what does it mean if we have a confidence interval between 0.175 to 0.225? It means we are 95% confident that the interval from 0.175 to 0.225 captures the true population proportion of people who would answer that question correctly. So we're not making a guarantee, right? We're saying we are 95% confident. Well, what must the actual percentage have been from their sample? Well, it's going to be whatever fell in the middle of 0.175 and 0.225. And so the way we find the middle there is to average those two numbers together. 0.2 was our point estimate because it falls directly in the middle of the two boundaries of our confidence interval. Well, what was our margin of error? 0.025, because 0.2 minus 0.025 gives me 0.175. 0.2 plus 0.025 gives me the other boundary on the confidence interval, which is 0.225. All right, and question number 3. If people guess one of the 4 choices at random, it would make sense that we should have about 25% of the people who get the answer correct. Does this interval provide convincing evidence that less than 25% of all U.S. adults would answer this question correctly? What we're looking for is, was 0.25 included in this confidence interval? And it wasn't. All the plausible values in the 95% confidence interval are below 25%, right? The highest percentage allowed in our confidence interval is 22.5%. Therefore, the interval does give convincing evidence that less than a quarter of all U.S. adults would answer correctly. Okay, so let's talk about a little bit of just notation here. Okay, so below we have a normal curve, which also means a bell-shaped curve. And it says color in the area of the curve representing alpha for a 95% confidence interval. So what is alpha? Alpha is the percentage of samples that would fall outside your confidence interval, or in other words, they would give you false results. They don't truly represent what's happening in the population. So if I have a 95% confidence interval, that means that 5% of samples will give me 5 false results. Okay? So if I mark that off on the graph, I'm splitting that into 2 pieces because that means 2.5% of my samples would be too low and 2.5% of my samples would be too high to actually show me a true picture of what the population is doing as a whole, right? So when it says example 2, compute the critical value Z alpha over 2. Again, alpha is 0.05. The reason we're splitting that in half is because we're assuming half the samples would be too low, half the samples would be too high. So alpha over 2 is 0.05. What it's asking us to do is to find the Z-score right here. Okay? And technically, it will be the same as the Z-score over here. It's just the Z-score on the left will be negative. So we typically go ahead and find the positive one. So how can we do that in our calculator? We do that by using the inverse norm button. And just to remind you where that is, okay, It is in the distribution menu. So I'm clicking the blue second button, and then VARs, and right there is inverse norm. For the area, I'm putting 0.975. Why am I doing that? Because that leaves out the 2.5% of samples that are too high, right? My mean should be 0 because we're dealing with z-scores, and my standard deviation should be 1, again, because we're dealing with z-scores. And I paste that in, and boom, my z-score that represents the upper limit of my confidence interval would be roughly 1.96. Okay? That is not something that I will ever ask you to do by hand. We'll do one more like this. So example 3 says compute the critical value, z alpha over 2, that corresponds to a 90% level of confidence. Well, if we are 90% confident, that means 90% of our samples will give us good results, 10% will not. So alpha is 10%. However, when we split that in two, that means 5% will be too low and 5% will be too high. Okay? So in our calculator, we are doing inverse norm, 0.9501, and that gives us a z-score on the curve of 1.64, which would be somewhere in this ballpark. Okay? And we're not going to do example 4 because it's exactly the same. Okay, so what are the different types of confidence intervals that we typically build? Sometimes we build a confidence interval for the mean, and sometimes we build a confidence interval around a proportion. So let's talk about some Hershey's Kisses. So when you toss a Hershey's Kiss, it sometimes lands flat, and sometimes it lands on its side. What proportion of tosses will land flat? So in order to truly answer this question with 100% confidence, we would have to buy every Hershey's Kiss in the world. We would have to flip them all and see which way they landed and recorded our results. None of us have the time or the money to do that. So instead, let's pretend that we got a random sample of 50's Hershey's Kisses. And we're going to look at what happens from that sample and then build a confidence interval. Okay? So let's say we flip these Hershey's Kisses and we find that 42% of them, or 0.42, land flat. That is going to be our point estimate. And again, we're calling it an estimate because it came from a sample, right? We can't verify that the entire population would have the exact same number. So what is our population? All Hershey's Kisses. If we had that information, we would have a parameter, and that parameter would be represented by the letter P for proportion. However, we are taking a sample of 50's Hershey's Kisses, so we are going to have a statistic, and so that symbol is going to be P with a little hat on top of it. So it still means proportion, but that little hat just tells us that it came from a sample. Okay? Was the sample a random sample? Yes, we know that because it tells us in the instructions. Why is that important? If it's not a random sample, I can't verify that my results really represent what's happening in the whole population, right? So, for example, if I got all my Hershey's Kisses from the same bag, what if that was just a bad batch of Hershey's Kisses? I would need to randomly sample several bags, maybe even 50 different bags, and pull one Hershey's Kiss out of each one. Okay? So what's the formula for calculating the standard deviation when we're dealing with a proportion? You have seen this before, and now it's coming back around. So this formula right here is our standard deviation, okay? The reason it's important is because it tells us how far spread out our distribution of samples will be, okay? How do I know that I'm allowed to use this formula? Well, in order for that to be true, I have to be dealing with normal data, or in other words, bell-shaped data. The reason I can assume that that is the case is because n times p times 1 minus p in this case happens to be greater than or equal to 10. Okay? I also have to know that my data is independent, which means it's less than, I have 10% written here. That is generally considered okay, but I believe my math lab asked you for 5%. So we'll say it was less than 5% of the population of all Hershey's Kisses. Okay? Now that we have verified that, we can calculate our standard deviation. So again, I plugged in 0.42 for P, which means that 1 minus P would be 0.58. And when I typed that formula in my calculator right here, it gave me a standard deviation of 0.0698. All right. So how does that help us? So we are going to skip down to question number 9. Okay. We actually use the standard deviation to help us calculate the margin of error for our confidence interval. So how wide is our interval going to be? So the formula for the margin of error is we take our critical value, which is our z-score that we talked about just a second ago, and we multiply it by our standard deviation. So if you have a 95% confidence interval, we actually already found the z-score for that. It was right back up here, and I'll scroll back up and show you that. So for our 95% confidence interval, our z-score was 1.96. We found that right here. So we are taking that 1.96 and we're multiplying it by our standard deviation, which we found to be 0.0698, and that gives us a total margin of error of 0.137. So how do we now build our confidence interval? We take our estimate from our sample, which was 42% or 0.42, and we are going to first subtract 0.137 from that number. That gives us a lower limit of 0.283. Then we're going to also add 0.137 to 42%. That gives us an upper limit of 0.557. So how would I interpret this interval? I can be 95% confident that the true percentage of all Hershey's Kisses that would land flat is somewhere between 28.3% and 55.7%. And here's what you will notice. The more confident you want to be, the less accurate you will be. Okay? So if I wanted to say 99% confident instead of 95% confident, that margin of error would have to get larger, and that would make these numbers right here farther apart. So it would make my confidence interval bigger. So it's kind of a trade-off. We want to be accurate, but we don't want to be, ending up with confidence intervals that are so wide that they have no meaning, right? All right. So right here, I have written down for you all the formulas that I just used. However, I do want to skip down and do a little working with these formulas. This example right here is very similar to the ones that we just did. Okay? Okay, so how might I be asked to use the margin of error formula? You might see something like this. So in example 1, a researcher wishes to estimate the proportion of adults who have high-speed internet access. What size sample should be attained if she wishes the estimate to be within 0.04 or 4% with 90% confidence if, part A, she uses a previous estimate of 0.32%. Or excuse me, 0.32, which is 32%. So let's break this down. The margin of error formula can actually be used to give us an idea of what sample size we would need to make some calculations. That 0.04 is the margin of error that she wants. So she wants to make sure her confidence interval is not too large. So that's why I'm plugging in 0.04 for E in this formula. The other thing I plugged in is my proportion estimate. So she is assuming that as far as she knows, it is 32% of people who have high-speed internet access. So for P, we're plugging in 0.32, which makes 1 minus P, 0.68. Okay, what am I plugging in for Z alpha over 2? Well, if we want a 90% confidence interval, that means alpha is 10%. So 10% of our samples would be bad, and then 10% divided by 2 is 0.05. So that's how I got this Z 0.05 right here. How do I calculate Z 0.05? I go into my calculator and I do inverse norm, 0.95, 0, and 1. And that spits out this 1.64 as that Z-score for me. Okay? So how do I solve this formula right here? Well, I would start by taking 1.64 and dividing it on both sides. And that would give me 0.02 0.439. Okay? How do I now get rid of the square root in the formula? I would square both sides. How do I get n by itself? Well, I'm going to multiply n on both sides. And finally, I'm dividing this big long decimal on both sides. So what would my sample size need to be? I would need at least 366 people. Okay? Part B is just a little bit different. What if she doesn't use any prior estimates? So what if she just literally has no clue what percentage of adults have high-speed internet access? We are going to estimate that P times 1 minus P is 0.25 and plug it in the formula right there, and then the solving will be exactly the same everywhere else. Okay? Okay, so let's talk about how you can do some of this in your calculator. Now, your calculator will not calculate sample size for you, but it will build you a confidence interval. So what I can do if I want my calculator to build me a confidence interval is I can go click the stat button and scroll over to test. Okay, so let me do that just quickly. Okay, so stat is right here in the middle. That's what I'm clicking. So stat, I'm scrolling over to the right twice to test. And for this example, I'm going to use the 1 proportion z-test. I think this kind of goes without saying, but if you aren't dealing with a proportion, you wouldn't use this test, you would use something else. So there's my 1 proportion z-test. What do I plug in here? It will pull up for me. Let's look at our example. Oh, excuse me, and I accidentally clicked test instead of interval. I'll go back and fix that in just a second. It tells me in the example, a random sample of 1,003 adults in a certain large country were asked a question. Do you pretty much think televisions are a necessity or a luxury you could do without? That is my sample size right there. Of those 1,003 people, 521 indicated that televisions are a luxury. Okay? So let me go back to my calculator and actually click the right button this time. So stat, test, 1 proportion z interval. We'll get to test in the next unit. X is going to be the number of people who are considered a success. So in this case, the number of people who called it a luxury. So 521. N is our total sample size, which is 1,003. And then the confidence level in this example, it said was 90%, so 0.90. And when you click calculate, it spits out several things for you. So the first thing it spits out, these two numbers are your confidence interval, right? That's your lower and your upper limits. This right here is your point estimate. So that was the proportion of people from your sample that considered television to be a luxury. Okay? So again, a lot quicker to use your calculator when you can. Alright, so what if I'm not dealing with a proportion? What if I'm dealing with an average or a mean? Well, we can do that too. Okay? So cuties are pretty tiny, but how small are they? Today, let's pretend you are weighing a random sample of cuties and build a 95% confidence interval to estimate the average weight of all cuties. So what is the point estimate? That would have come from our sample. Okay? Let's say that from our sample, we got an average weight of 78.4 grams. Okay? So that is a statistic because it came from a sample of 27 cuties, right? If we were somehow able to buy all the cuties in the world, then get their average, we would call it a parameter, and we would use that Greek letter mu to stand for the mean. Okay? Was our sample a random sample? We are going to assume that it was, simply because if we don't, we can't eliminate bias. Okay? Well, when we are dealing with a mean, or x bar, we have a different formula for our standard deviation. And that's, we take the standard deviation of our population and we divide it by the square root of our sample size. Okay? So what condition do we have to check in order to use this formula? We have to check the 10% condition, or again, I believe my math lab asks you for 5%. We have to make sure it's independent, and 27 cuties is definitely less than 5% of all the cuties in the world. So we can assume that our results are independent. Okay? So here is the problem. For our formula, we are supposed to use the population standard deviation, and we don't have it. So instead, we are going to use our sample standard deviation, which is right here. Okay? And I have given that to you. That is something that I would have calculated by putting the raw data from those 27 cuties in the calculator and letting it give me the standard deviation. So the standard deviation was 7.22. When I divide that by the square root of 27, I get 1.39. That is going to be the standard deviation of my sampling distribution, or all possible samples, which is what I'm looking at for a confidence interval. Okay? Question number 7, would it be appropriate to use a normal distribution to model the sampling distribution of X bar? We don't really talk about normal probability plots in here. That is something that you can check to verify it, but typically we are looking for a sample size of at least 30, and while our sample size wasn't exactly 30, it was pretty doggone close, so we can assume that it's normal. Okay? Now, here is something that is slightly different. When we are finding a confidence interval for a mean instead of a proportion, we use, instead of a z-score, we use what is called a t-score. Okay? So where a normal distribution of z-scores looks like this when we graph it, so it's a bell curve, right? Sort of like that. A t-curve looks very similar, but it's narrower in the middle and it has more room in the tails. And the reason for that is because when we're dealing with sample means, outliers can have a bigger impact, and so we leave more room for error out here in the tails of the graph, and there's less samples that fall in the middle. Okay? So instead of seeing me say like z alpha over 2 or z star, you're going to see me say t star or t alpha over 2. Okay? So number 9, what t-value is needed for a 95% confidence interval? The way that we find that is by using, instead of inverse norm on our calculator, now we're going to use inverse t. Okay? And so just to remind you what that looks like, if this was my curve, and I know that it's narrower, right? And 95% of my samples are good, that means 0.025 were too low, and 0.025 were too high. So we are looking for the t-score that has 0.975 or 97.5% of samples that fall below that line right there. So I'm doing inverse t in my calculator. Okay? And I'm putting in 0.975 as the area. And it asks me for something called degrees of freedom, which you have probably never seen before. If we have 27 cuties in our sample, our degrees of freedom is going to be 26. Okay? And so when you type that in the calculator, it gives you a t-score of 2.06. Well, how do we use that to calculate our margin of error? Much like we took the z-score times the standard deviation in our previous examples, we are now taking the t-score times our, we call it standard error instead of standard deviation. But it's this number right back up here that we calculated, that 1.39. So when we take 2.06 times 1.39, we get that our margin of error is 2.86 grams. So let's use that to build our confidence interval. So the estimate from our sample was that these oranges weigh 78.4 grams. But we know that could be off a little, so we build in our margin of error, and when I subtract 2.86 from 78.4, I get that the lower limit for the average weight of all cuties would be 75.54 grams, and the upper limit comes from adding 2.86 to 78.4, and that gives me 81.26 grams. So how would I interpret that? we are 95% confident that the interval from 75.54 to 81.26 grams captures the true mean weight of all cuties. Okay? Alright, so again, can I do this in my calculator? Absolutely, you can. I'm trying to see if I have an example, and I don't think that I do, so we'll do that same example in your calculator. So what you are going to do when you are dealing with means is you are going to go back to the stat button, go over to test, but this time, instead of 1 proportion z interval, you are doing a t interval. Okay? You're going to go over to stats, and you can put in your information right there as needed. Okay? Or if you were to have the raw data, that is also an option, but we don't usually have the raw data. Alrighty. Okay. So let's talk a little bit more about the t-distribution and what it looks like. So as we discussed, the t-distribution is a little bit skinnier than the normal distribution. It's specifically used when we are building confidence intervals for means. Why is that? It's because when we build confidence intervals for means, a couple reasons, outliers can impact the mean very, very heavily, where they don't so much when you're dealing with proportions, because proportions are generally just a count of people who fall in a category. So it's kind of a yes or no situation. It doesn't matter how far out of that category they fell. They either fell in it or they didn't. Outliers aren't that big a deal. With means, outliers can be a huge deal, right? Because if I have, a small sample size, and let's say my sample size is 5. Let's say we had 4 people who all made an 80 on a test, but then we have that 5th person who made a 30, right? They're an outlier, but the average is going to drop dramatically because of that one person who made a 30. And on the whole, it makes that class of people look like they may not really know what they're doing when actually it was just that one person. So we use a t-distribution because it allows for larger amounts of people to fall in the tails. So for more people to represent error, right? It's used when we don't know the true population standard deviation. And it is frequently used with sample sizes less than 30. And again, that's what we just talked about, because the smaller your sample size, the more an outlier matters. Okay? However, if you can get a good large sample, the larger your sample size is, the closer that t-distribution will get to that true normal distribution, right? Because the bigger my sample size, the less error I have to account for, because one outlier is kind of absorbed into everybody else. It doesn't matter as much. Okay? And so in case you're curious of the formula, we have calculated z-scores in here by hand. I'm never going to ask you to calculate a t-score by hand, but in case you were curious what the formula is, there it is. Okay? Alright. So that is the end of our discussion on Unit 9. Please let me know if you have any questions.